So when we condense these logarithms, if you've got a log of x plus a log of y, that will condense to one logarithm of x over, I'm sorry, not x over y, but x times y. If you have a log x minus a log y, that will condense to one logarithm with a fraction behind it. These are the properties of logarithms that we worked on last Thursday and Friday when you guys were not here. So please make sure that you go back and do that. Now, once we condense, if we need to, because sometimes you don't have those scenarios, once you get a logarithm equal to a logarithm, then you're going to set the m value equal to the n value, the m value equal to that n value. Whatever it is, that's what you're going to do. Computer's closed, fellas. All right. Now, the last thing, you have to check for extraneous solutions, because sometimes you solve for an answer and you have to throw it away. All right. I'm going to show you how to check for your extraneous solutions. So the first couple of examples, 1 through 3, are the ideal situation. Okay. I have a log base 5 of something equal to another log base 5 of something. Do y'all agree? So basically what I do is I drop the log base 5s and I set 5x plus 9 equal to 6x. And then I solve that equation for x. So I'm going to subtract the 5x. That gives me 9 equals to x. Now, before I say that is my number, this number and this number have to remain positive. So when you check for extraneous solutions, when you take the 5x, so 5 times 9 plus 9, that stays positive. Do y'all agree? I don't care what positive number it is, as long as it stays positive, we're good. And then 6 times 9 stays positive. So I can say, yes, that is my answer. Now, if I had taken my answer and plugged it into either one of these places and either value turned into a negative, you have to throw that out. And I do have an example somewhere in here where we do have to throw our solution away. So example 2, I have a log base 2 equal to a log base 2. You've got a logarithm equal to a logarithm. So when that is the case, I'm going to take this value, set it equal to this one. Drop the logarithms. So 1 minus 4n equals to 2n plus 43. Do whatever it takes to solve it. I'm actually going to add the 4n because I like positive n's. Then I'm going to subtract 43 from both sides. Now, if you want to solve this going in a different direction, that's fine. But at the end of the day, when we get to this point, our n value should equal to negative 7. Now, I have a negative answer. I don't care that my answer is negative. What I care about is when I check my solution, if it makes this value negative, I have to throw it away. So 1 minus 4 times negative 7 becomes 1 plus 28, and 1 plus 28 is a positive answer, correct? So we're good here. I also have to check it over here. 2 times negative 7 plus 43. Negative 14 plus 43 will remain a positive number. So I can keep negative 7 as my answer. I don't care what my answer is. The biggest thing is, does that answer create negative values here? Because these numbers cannot be negative. All right, everybody got a calculator with the log button on it. I want you to see what you get when you type in log 6 versus log of negative 6. For which one? You should get the domain error because this value has to be positive. That one's not. So that's why we have to check our answers, because if any of our answers cause this, or this to be a negative, we have to throw it away. So example number 3 does give us a situation where we have no solution. I have a log base 9 equal to a log base 9, so I'm going to take these numbers and set them equal to each other. So 6 minus 3w equals to negative 2w. I'm going to add 3w to both sides, and that gives me 6 equals 2w. Now that looks like an acceptable answer, correct? But when I plug it back in, 6 times 3 times 6, that gives me 6 minus 18, which is negative 12. That means this is not a legitimate answer. Now, I do have to caution you, sometimes you can plug in an answer and it works here, but it won't work here. So I would make sure that I check every place, and that still equals to a negative number. These values always have to remain positive. So I don't care what your answer is, if you plug it in and it makes it negative, then you have to throw it away. Now, in the next few examples, we have more than just a logarithm equal to a logarithm. So we're going to have to condense these so that we do have just a logarithm equal to a logarithm. Now, up here, I told you if you had a log plus a log, you multiplied these two numbers together, or these two groups, whatever they are. So in this scenario, I have a log plus a log. That changes to one logarithm with y plus 4 or y plus 5 times 4 behind it. You pull these two numbers together with multiplication. Now, although this is being multiplied together, I have a log, one log equal to one log. Do y'all agree? So I am going to set these numbers equal to each other. So y plus 5 times 4 equals 72. I need to distribute that 4, which would give me 4y plus 20 equals to 72. Subtract your 20 and you get 52. Subtract 20 from both sides. Divide both sides by 4 and you get 13. Now, I have 3 logarithms up here, but there's only one logarithm that has a variable in its mix. Does that make sense? So I only have to check this one. There's no place to put 13 here. There's no place to put 13 here. So as long as 13 plus 5 stays positive, we can keep it. 13 plus 5 is 18. So 13 is a legitimate answer for that problem. Now, there is another property that I did not write at the top of your page. And this one is called the power property. And it basically says if you have a log base b of x, you have a multiplier, a times the log. You can take that a value and make it your exponent. So you can rewrite it as log base b of x to the a power. Because in the next couple of examples, in 5 and in 8, because we're not going to do 7, but in 5 and 8, we do have some multipliers that we have to deal with. Now, although I have a logarithm equals to a logarithm, I cannot have that multiplier out in front. So I'm going to use my power property. And I'm going to move that to be the exponent on that number. So I have log base 7, 4 to the third power, equals to log base 7 of 4a minus 8. Now, I have a log base 7 equal to a log base 7. So I'm going to take this number and this number and set them equal. I'm going to drop both log base 7s. So 4 to the third equals to 4a minus 8. 64. 4 to the third is 64. I'm going to add 8 to both sides, so that would be 72 equals to 4a when you add 8 to both sides. So a is going to be equal to 18. Now, I have to check my answer. This number has to stay positive. There's no place for me to plug in 18. This number also has to stay positive, and I do have a place to plug in 18. So 4 times 18 minus 8, that's 72 minus 8, and that outcome, I don't care what it is, but it's going to be positive. So I can keep 18 as my answer. In number 6, if y'all have questions, y'all make sure that you stop me. In number 6, I have a logarithm minus a logarithm. At the very top, I said if you have a logarithm minus a logarithm, you write it as one logarithm with a fraction behind it. So I'm going to have 1 log base 4 of 68 divided by 4 behind it. This number divided by this one. I don't care if those numbers have x's in them. You're still going to put whatever in the group divided by whatever in the other group. Now, I had to condense that so I could create the log equals log scenario. So I'm going to take this number at this point and this number and set them equal. So 68 over 4 is equal to 3n plus 11. What is 68 divided by 4? 17. So 3n plus 11. I'm going to subtract 11. That gives me 6 equals to 3n. So n should equal to 2 when you divide both sides by 3. Now, this number has to stay positive. This one has to stay positive, and so does this one. But this last one is the only place you have to plug in your answer. So 3 times 2 plus 11 has to be positive, and it is. 6 plus 11 would stay positive. So I can keep that 2 as my answer. Now, number 8, we do have a multiplier. So I am going to put that multiplier back. It's the first thing I always look for. Anytime you have something multiplied by the logarithm, you always put that back as the power. So that becomes log base 3 of 2p minus 5 equals to log base 3 of 6 squared minus log base 3 of 4. All right, so I used my power property. I need to condense this into one logarithm. So I'm just going to bring the left-hand side down. And I need 1 log base 3. Do I multiply the 6 squared and the 4, or do I divide it? I divide it. A log minus a log would become a division problem. So I have created the ideal situation. Log equals to log. So I'm going to take the numbers, set them equal. So 2p minus 5 equals to 6 squared over 4. 6 squared over 4 is equivalent to 36 over 4, and that reduces to 9. Do y'all agree with that part? All right, so 2p minus 5 equals to 9. I took this over here and just kind of simplified it out. I'm going to add 5 to both sides. 2p equals to 14, so p equals to 7. All right, before I say that is my answer, before I type that answer into Math Excel, I need to go across all the logarithms in the original problem and see if that 7 makes any of them negative. Well, the only place to plug in the 7 is right here. There is no p on the second or third logarithms. So as long as 2 times 7 minus 5 ends up being positive, I can keep it. That's 14 minus 5, and that would be positive 9. So 7 is my answer. Now, typically, I don't write that number. I just say 14 minus 9 is positive because that's what I want. Because a lot of times students will accidentally type in 9 as the answer as opposed to 7 because 9 was the last number that she got. All right. Any questions about the type 1 problems? Now, I do have a video and it's got these last 2 problems in it. You can go in, fast forward to those. All right. Type 2 logarithms. They're a little bit different. Okay. Because what we're going to do is we are going to create, excuse me, we're going to create a logarithm equals to a number. And then once we condense and isolate that logarithm, we are going to write this in exponential form. Then we're going to solve and check for extraneous solutions. This value cannot be negative, neither can this one. Okay, so what we want to do is we want to condense and isolate. So we want log base b of some number x equaling to another value. Now, once we get one logarithm equal to a number, we're going to rewrite this as b to the y equals to x. You're going to grab that base number, raise it to that power, and set it equal to this number. And then you're going to solve this problem, okay? And I'll show you how. The good thing about this is most of these problems work out the same way every single time once you set it up correctly. So what we want is one logarithm equal to a number. We're going to take that form out, write it this way, and then we're going to solve that problem. Okay, everybody got your calculator? Are you familiar with your exponent button on your calculator? Not just the x square button, but the exponent button on your calculator. Some of you actually have like an x to the y power, or maybe you have a y to the x. Some of you have a little key that looks like this. If you're not sure where your exponent button is, do not leave this room without me helping you. So here, I have the perfect scenario. I have a logarithm equal to a number. So I'm always going to grab my base, raise it to this power. Notice I went to the other side of the equal sign. So 2 to the 6th power equals to whatever is inside that parentheses. We're going to set it up that way every time. We're going to do several of these, so you'll kind of get used to the way you set them up. 2 to the 6th power, what is that value? 64 equals to x minus 4. When you add 4, you get 68 equals to x. Now, I have to decide if I can keep that answer or not. So if I plug 68 here and I get a negative outcome, I can't keep 68. So 68 minus 4 does give me a positive outcome. So 68 would be my final answer. All right, number 12. The problem I have, we are supposed to isolate the logarithm. So I need to move that 7 to the other side. So I'm going to add 7 to both sides because it's outside the logarithm. So I have log base 3 for x plus 8 equals to 4. Negative 3 plus 7 is 4. Now I have a logarithm equal to a number. So I will always grab the base, raise it to this power. So 3 to the 4th power equals to whatever is inside that group. Now, this answer is going to be a fractional answer, so do not give me the decimal. 3 to the 8th power, or 3 to the 4th power is 81. I'm going to subtract 8, and that gives me 73 equals to 4x. And when we divide both sides by 4, we get 73 over 4 equals to x, because those 4's will cancel. Now, I have to make sure that when I plug 73 over 4 into that value, it stays positive. So 4 times 73 over 4 plus 8 should remain positive. Well, the 4's will cancel, and 73 plus 8 is a positive outcome, so I can keep that ugly fraction. All right, we're going to stop right there, and we will pick up with number 13 after lunch, because I did hear the... All right, so number 13, pick up where we left off before lunch in just a moment. Didn't realize my tablet had turned off. If you notice, you have a log plus a log. So what's going to happen here is we have to combine these two together. So the rule that I gave you, a log plus a log, you multiply these values together. So 1 log 2x times x minus 5 equals to 2. So that was the property. A log plus a log becomes 1 log with everything being multiplied together. Now, we haven't had one of these just yet without a visible base, okay? The 2 we had up here, we had a base 2, we had a base 3. When there is no visible base, there is an understood 10 that is your base. So we're going to, so like over here, there will be little 10s right there. You don't see them, but they're understood to be there. So we're going to take 10 to the second power equals to 2x times x minus 5. So now we have to solve this problem. So 100, 10 squared is 100. I'm going to distribute my 2. That gives me 2x squared minus 10x. I'm going to set it equal to 0 because this is a quadratic. So this is the first time we've come across a factoring problem. I'm going to subtract 100 from both sides. Now, before I try to factor, I look at all three numbers, 2, 10, and 100. I can reduce all of those by 2. So I'm going to come over here in the margin. If I divide every single number by 2, that gives me 1x squared. 10 divided by 2 is negative 5x. And 100 divided by 2 is 50. I would much rather factor with these numbers than these numbers. So when you come across a problem that needs to be factored, in these particular logarithmic lessons, they are going to factor the way they should. So factors of negative 50 that add up to negative 5 are negative 10 and positive 5. Negative 10 times 5 gives me negative 50, but negative 10 plus 5 gives me the number in the middle, which is negative 5. So I've got to come up with that combination that works. Once I get them factored, I set each factor equal to 0 and I solve it. So x equals to positive 10, x equals to negative 5. Then I have to check, can I keep both of those answers? I have to check this value, 2x, and I have to check x minus 5. So when I check 10, 2 times 10, that is a positive outcome. 10 minus 5, that would be for this one. That's also a positive outcome, so I can keep 10. But watch what happens when I plug in negative 5. 2 times negative 5 is not positive, so I don't keep that one. As soon as I find a spot where my answer makes the outcome to be a negative number, I stop and I don't use that answer anymore. Even if you checked it here, negative 5 minus 5 does not equal to a positive number. It equals to negative 10. So regardless of where you put it, it's not going to work or be a legitimate answer. So for number 14, we are going to use our power property. And we're going to put that multiplier back as the exponent. So I'm going to rewrite this first as log of x squared minus log of 4 equals to 2. I'm going to take these two logarithms and write it as one logarithm. But would I put x squared times 4 or x squared divided by 4? Divided. Now, I'm going to take that base 10, raise it to this power, so 10 squared, and then I'm going to set it equal to whatever's inside that group, which is x squared over 4. So this becomes 100 equals to x squared over 4. So I'm going to multiply both sides by 4 to get rid of that denominator. So 4 times 100 is 400 equals 2x squared. How do you get rid of an x squared? Take the square root of it. Now please do not forget, when you use the square root property, there is a plus minus component. So the square goes away, and I put a plus minus in front of that. Now, if you type the square root of 400 in on your calculator, you get exactly 20. So I have two answers, x equals to positive 20 and x equals to negative 20. This is my issue. This number right there has to stay positive. But when you plug positive 20 in, life is good. But when you plug negative 20 in, it doesn't turn back into a positive. So we only have one answer for that particular question. All right, we're going to do one more, and I will let you pick 15 or 16. All right. Now, for 15 and 16, if you want to see 16, 16 is done on the full video that I did this morning. So you would have access to that, and it's just called Logarithm Equations Type 2. So you can find it on PLP. I do not have any multipliers out in front of my logarithms, so I do not have to create any exponents. Now, I have a log plus a log. I need to write it as 1 log base 6. Do I multiply the x plus 9 in the x, or do I divide it? When you have a log plus a log, do you multiply them or divide? Multiply. So I'm going to take the x plus 9 and multiply it by the x. Notice how I started with 2 logarithms. I now have 1 logarithm. Once you get those combined down to 1 logarithm, we're going to raise 6 to the 2nd power, and that is going to equal to all of this. So 2 things I have to do. I'm going to square 6, which is 36, and I'm going to distribute the x. So x times x is x squared, and x times 9 is 9x. When I distributed x, I end up with an x squared. So I am going to have to move the 36, set it equal to 0, and factor. Now, like I said earlier, if you end up with a quadratic, you should either be able to do the square root property, which we did right here, or you should be able to factor it. Most of these, if not all of these, at your level are set up to where they will factor. So I need factors of negative 36, that when I add them together, I get positive 9. So that would be 12 times 3, negative 3, that gives me negative 36. And when I take 12 and add negative 3, I get positive 9. So I get x plus 12 and x minus 3. That will actually give me 2 answers. X plus 12 equals to 0. X minus 3 equals to 0. So x equals to negative 12 and x equals to positive 3. One of these answers needs to be thrown away. When you go back and check, this number has to stay positive and this number has to stay positive. Well, when I plug in negative 12 plus 9 does not equal to a positive number. So negative 12 is out. I'm going to start again. 3 plus 9 does stay positive, so that checks out. And then I just need to put 3 right there, so that stays positive as well. So I can only keep the one answer. Any questions about solving logarithms? Because we did 2 different types. If you have a log equal to a log, you just set the numbers equal. And these, we did 1 logarithm equal to a number, and then we had to rewrite. All right. So if you flip the page, now like I said, if you need to see number 16 or you want to see number 16 just for additional resource, it is on that video. I am holding you responsible for watching those videos and keeping up with what we do on the days that y'all are not here. All right, I think this should be your next page. Is that correct? Okay. So now on this page, what we are going to do is we are going to solve exponential equations by using logarithms. So we're going to have to press the logarithm button on our calculator this time. Okay. Now, I believe we all got through this part Monday and Tuesday of last week before we went on this new schedule. So using a common base to solve an exponential problem. If you notice, this is a base 5. I can change 25 to 5 squared. Do y'all agree that 25 is equivalent to 5 squared? 5 times 5. So what I'm going to do is I'm going to rewrite 25 as 5 squared. That gives me a like base. And if that's the case, I drop the bases and I set my exponents equal. So n plus 10 equals to 2 and n equals to negative 8. The great thing about solving exponential equations is the exponent can be anything. Now, number 2 is a little more challenging, but we can create a common base. The base that 9 and 27 have in common is a 3. I can take 9 and write it as 3 squared. I can take 27 and write that as 3 to the 3rd power. So I can change both of these numbers to a base 3 number. Different exponent, but still a base 3 number. So I'm going to take 9 out and I'm going to replace it with 3 squared. Now, there's already an exponent there, so I'm going to multiply those exponents together. I'm going to take 27 out and replace it with 3 to the 3rd. And I will multiply that 3 by the exponent that was in the original expression. Now that I have like bases, I'm going to set my exponents equal to each other. So I have 2 times a plus 2 equals to 3 times 4a minus 2. Distribute your 2 on the left, 2a plus 4. Distribute the 3 on the right, which would be 12a minus 6. It doesn't matter which way you go with your a's or your numbers. I'm going to subtract 2a and move it to the right. So that gives me 4 equals to positive 10a minus 6. I'm going to add 6 to both sides. So that's 10 equals to 10a. So a will equal to 1 when you divide both sides by 10. Exponents are great because exponents can be anything. You do not have to necessarily check for extraneous solutions. Did we use a logarithm at any point in example 1 or 2. Okay. So now what we're going to do is we are going to use logarithms, because what if you cannot create a common base? Okay. So let's say we had 5x equals to 14. There's no way I can change 14 to 5 squared or 5 to the third power. Do y'all agree? Okay. So what we're going to do is we are going to isolate that base. So what we want is we want b to the x equals to y. We want to isolate the exponential expression. So best case scenario, you want it to look like this. If it doesn't look like this, you're going to have to make it look like this. All right. Then what we're going to do is we're going to take the logarithm of both sides. So we're going to write log base b of x equals to log of y. So first step, isolate. Now, keep in mind the exponent can be anything. If it wants to be x plus 2, that's fine. So the exponent can be anything, but I just need a base number with an exponent. Okay, once I do that, I'm going to take whatever my exponent is. The exponent is not always going to be x. It could be an x plus 2, an x minus 4. You're going to use the power rule and go backwards. You're going to put that out in front as a multiplier. So we're going to have x times log of b equals to log of y. And then we're going to solve that. We're going to divide both sides by log b. So x is going to equal to log y divided by log of b. And then we're going to type that in. Now, there is a little bit of redundancy once you get to a certain point. So for example 3, we are going to, I have my b to the x equals y. I have that by itself, so I'm good. So I'm ready for step 2. I'm going to take the logarithm of both sides. The next step, once I log both sides, when I am to that point, what you do next is pretty much the same every time. Whatever your exponent is, I don't care if it's just x or if x minus 4, x plus 2, we're going to pull that out in front as a multiplier. And then we're going to divide both sides by the logarithm attached to x. So the log 2 and the log 2 will cancel and leave me with just x. Now, when you type this in your calculator, log 61 divided by log of 2, you should get 5.9307. Do that on your calculator. I will pause. So for this one, we have the ideal situation. Even though our exponent is bigger than just an x or just an m, that's okay. As long as you have b to the exponent equals to a number, we're going to put a logarithm out in front of both sides. That goes back to what you do to one side, you must do to the other. So I can log both sides. Once you get to that point, if you put that logarithm, then you're ready to tell me the next step, which is to take the exponent, whatever it is, and move it out in front as a multiplier. So that gives me m minus 7 times log of 8. Notice how I kept my exponent as a group. And that is equal to log of 92. Since log 8 is being multiplied, I'm going to resist the urge to distribute, and I'm going to divide both sides by log 8. At this point, you should have m minus 7 equals 2.1745. I got 2.7 or 2.1745 from taking log 92 and dividing it by log 8. What do you think the last thing should be in order for me to get m by itself? What should I do with the 7? Add it to both sides. So m is actually going to equal to 9.1745. Any questions about that one? All right, we have just a few more of these that we're going to do. And then you will need to watch the video for the very last section. And then we will get those packets out for the unit circle. So here, I have this pesky little 4. I need b to the x equals to y. I do not need something times b to the x. So I'm actually going to divide both sides by 4. 148 divided by 4 should give you 37. Once I get to this point, I am ready to log both sides. When you're ready to log both sides, that means that exponent is going to drag out in front. You're going to use your power property to move it. And then we will divide both sides by log of 7 to get the value of n. When you do that, you should get 1.8556 for n. All right. What has to move in number 6? Because it's not ready. You're not ready to log both sides just yet because something's in the way. What do you need to move first before you can log both sides? The 5. So I'm going to add 5 to both sides. That gives me 4 to an exponent. I don't care what the exponent is as long as I've got a base to an exponent. And that gives me 8. 3 plus 5 is 8. Now it is set up in the proper format for you to logarithm both sides. If you are ready to log both sides, your next step would be to take that 3w, put it out in front. I'm going to divide both sides by that log 4. That gives me 3w, because the log 4's on the left will cancel, equals 2. And when you take log 8 and divide it by log 4, you should get 1.5. Then I'm going to divide both sides by 3. So w is going to equal to 0.5. And like I said, exponents can be anything. You don't have to worry about these having extraneous solutions. All right. We're going to do 2 more problems on the next page. Number 7 is going to be one of them, and I'm going to let y'all pick the second one. I do have a video where all 8 of these problems are worked out, so if you need additional resource, it's there. But there is a reason I want to show you number 7, because this is actually a no solution scenario. And I want to explain to you why you might end up with a no solution scenario when I keep saying that exponents can be anything, okay? So here, the first thing I'm going to do is subtract the 7 because we got some stuff on the outside of that base in the exponent. So that gives me negative 4 to the x plus 1 power equals to 11. I can't even have that negative, so I'm going to divide by negative 1. So that gives me 4 to the x plus 1 power equals negative 11. So we've done all that kind of stuff before. We've got to isolate the base and the exponent. So now you're ready to take the logarithm of both sides. We're going to take that exponent, move it out in front. And when you get to this point, when you go to divide both sides by log 4, you get x plus 1 equals to domain error. When you try to type this in your calculator, it should give you the domain error message. The reason it does that is because this number can never be negative. And when we did that, we ended up with a logarithm of a negative number. So if you have the logarithm of a negative number, there is no solution for that. You will get domain error every time you press that on your calculator. Okay? So even though exponents have the ability to be anything that they want to be, positive, negative, 0 decimal fraction, does not matter. Sometimes they give you problems that just don't work. Okay? Now, we have 8 through 14. 8 through 14. Want to see 14? All right. So our goal is to isolate the base with the exponent. So the 3 and the 10 have to move before we can log both sides. So I'm going to subtract the 10 first. That gives me 3 times 8 to that exponent equals to 84. Divide both sides by 3. What is 84 divided by 3? So I had to do 2 moves. I had to subtract the 10 first, and then I had to divide by 3 to get the base and the exponent by itself. You can't have anything other than the base and whatever the exponent is. Now you are ready to log both sides. And from this point, it kind of goes, it does the same thing. Once you log both sides, you always move your exponent out in front. The next thing you will do is divide both sides by that logarithm on the left. So I end up with 3 minus 7n because the log of 8's canceled. When I divide log 28 by log 8, I should get 1.6025. From that point, I'm going to subtract 3. That gives me negative 7 equals to negative 1.3975. And then I'm going to divide both sides by negative 7. And that gives me 0.1996. And that is my actual answer. All right, any questions about that? All right, so double check me. You have one more section, which is E. Does it say what is E on the next page? Okay. Now,